Okay guys, welcome back. We've been talking about AC motors, in particular single phase AC motors for right now, and we've talked about, the winding on there and how it's, alternating, and we could imagine that as being rotating, and that the rotor inside there is going to want to rotate and, run at close to sync speed. It'll slip a little bit. Now, unfortunately for single phase machines, the winding in there doesn't cause the magnetic field to rotate. It actually just causes it to alternate. And because of that, the motor actually is incapable of starting. And if you've ever seen an AC motor try to start, if it doesn't have, the start winding, it sits in there and just sort of hums and it doesn't do anything. And the reason it doesn't do anything is because of that magnetic field. It's actually just alternating and not rotating. And so for single phase machines, at least, we need to do something in order to make that thing, actually rotate. And they do it by adding another winding in there, and it's called the start winding, also known as the auxiliary winding sometimes, guys. And it's sitting here mechanically 90 degrees, out of phase with the run winding. And I didn't draw the windings on there just to keep this drawing a little bit more neat, but it's going to be wired in parallel with the run winding, except for there's going to be a switch in series with it, and that is known as the centrifugal switch, okay guys, and that is usually located at the back of the motor. And what it does is it sits in there closed when the motor is off, and then when the motor starts up and starts running, it opens up sometime, during the start, usually at around 75% of the RPM, okay? And so it's really important to understand that that start winding is only in the circuit while the machine is stopped or while it's just starting up. Once it has started up, the centrifugal switch will open up and the start winding will come out of the circuit, and it'll be running on just the run winding. Okay, and so here I've drawn my start windings mechanically 120 degrees or 90 degrees out of phase with the run winding. And these two windings are wired slightly differently. And I'm not going to write it down, guys, here because it's in your notes here. There are going to be two windings 90 degrees apart, okay? The first winding, the run winding, is going to be low resistance and high inductance, okay? And so this is a red winding here is going to be heavy wire, low resistance, okay? And high inductance. And then the start winding is going to be made out of fine wire, guys. It's going to have a lot of resistance because it's fine wire, and it's going to have fairly low inductance, okay? And again, it's the start winding that's being disconnected from the circuit after it gets to about 75% rated speed. Now, what that happens is, so let's write this down. This guy here is low R, okay? High XL, okay? And this one is high R and low XL. Now, what happens is when I first start this motor, I'm going to have both windings in there, and because this one is low resistance, high inductance, it lags a lot, okay? The current lags a lot. This one here also lags. It is an inductor, but it lags a little. All right, guys? Now, it's important to understand that the magnetic pulse happens when the current flows, okay? Because there was a formula you learned in level 2. I know you've forgotten it. It's a magnetism formula, but it looked like this. FM is equal to IT, okay? And I'm not going to try to expect you to remember it, okay? But what this means is the magnetic force that you get from any electromagnet is the current flowing through it times the number of turns. And so it's important to remember that you're going to get the magnetic pulse here from your AC sine wave, not when the voltage appears, but when the current appears. Okay? And so if I looked at this, guys, and I had my AC waveform, okay, I am going to get two different pulses here through these two different windings. The first one is going to be the run, well, not the first one, but one of them is going to be the run winding. And I don't know why I drew this so small. Can you guys see it? Okay. So here's the red run winding current. Okay. We're going to draw it in here. Lagging a lot. Okay. So this is I run. And you're going to get the current through the start winding. It's going to lag a little. It is an inductor, so it is going to lag a little. Whoops, I don't want that pen. That pen sucks. All right, we'll do, where's my green? Where's my green marker? There it is. Okay, so there's the other current that you're going to get, guys. It's going to lag also. Whoops. Okay. I start. And if I look at those two currents and compare them to the voltage, guys, I'm going to get this, right? So let's say my voltage is here, E, okay? And I'm going to get I start. Sorry, I run. I don't know why I switched colors here. Okay, so pretend that's red. Okay, let's do it red. There's my run current through the red winding. Okay, it's lagging by quite a bit. And then I get my start winding. Also lagging by not near as much. And so what happens here when I first turn this on is I get a pulse in the start first, then I get a pulse in the run, then I get a pulse in the start, then I get a pulse in the run. And so what this is going to cause is a rotating magnetic field and not just a, flipping magnetic field. But it's important to also see that you're only going to get 30 to 50 degrees, okay? And there's a way better drawing of this, okay, guys, in your book already. All right, you can see the start winding current here, hits here. 30 to 50 degrees later, I'm going to get the current through the run lining. So you're going to get a north in the start winding, and then 30 to 50 degrees later, you're going to get a north in the run winding. And so you would kind of get this uneven rotation where this is 30 to 50 degrees, and then this is like 100 and, I don't know, I'm not very good at math, okay, but 130 degrees later or something like that, and then 30. So you're going to get a rotating magnetic field. It won't be particularly even, but it will be rotating, and that'll be actually enough to get this thing to run in the direction that you want it to. And once it's running and fires up, guys, this switch is going to open, and then the start winding will not even be in there. Okay, it'll be completely isolated from the circuit, and you will go back to having an alternating magnetic field, but that's good enough. Okay, once this machine is turning, it's going to follow this alternating magnetic field, no problem whatsoever. All right, guys? And so that is the resistance start induction run motor. It uses, a high resistance winding together with a high inductance winding to, simulate a rotating magnetic field. It's really important to remember that the centrifugal switch must open, and if it doesn't, the start winding will stay in the circuit. This start winding is not designed to stay in the circuit. It's only in there during startup, okay? But that is how we create a rotating magnetic field in a resistance start induction run motor. Come back and we'll talk about capacitor start motors.